This video is the reward for all your patience when we went through all of that theoretical quantum structure of the atom. I'm about to tie this to real experimental things. I'm going to tie electron configuration to the structure of the periodic table. And what I'm going to do is take characteristic groups from the periodic table, look at their electron configurations, and see if I can find some patterns. We know that all of the elements in a group have similar chemistry. Let's see how we can relate that similar chemistry to their electron configurations. Now, as I said in the last video, to do this, you're going to need to have a periodic table with you so that you can know how many electrons we're going to place. If you don't have a periodic table, pause the video and go get one. All right, helium is number 2, neon 10, argon 18, 36, 54, 86. So those are the number of protons in the nucleus. I want the number of electrons. These are neutral atoms, so the number of electrons will be the same as the number of protons. That's why for helium, the electron configuration is 1s2. There's the 2 electrons. Now, you can get ahead of me on this. I want you to pause the video and write the electron configurations for neon, argon, and krypton. Don't worry about xenon and radon. That's too much writer's cramp. We'll see a pattern before we get to those. Okay, go ahead, pause the video. All right, neon with 10 electrons. 1s2, 2s, 2, 2p, 6. Argon, 1s2, 2s2, 2p, 6, 3s2, 3p, 6. And krypton, 1s2, 2s2, 2p, 6, 3s2, 3p6, 4s2. What have I got there? 20, 3d10, 30, 4p6. All right, I'm starting to see a pattern form. What I'm going to do is look at not all of the electrons, but the valence electrons. I'm going to look at the valence configurations for these atoms. Remember, I defined in an earlier video that the valence electrons are the ones in the highest occupied energy level. So for helium, that's the first energy level. And the valence configuration for helium is 1s2. I'm showing only the electrons in the highest occupied energy level. For neon, the valence level is the second energy level. So its valence configuration is 2s2, 2p6. For argon, the highest occupied energy level is the third energy level. 3s2, 3p6. And finally, for krypton, highest occupied energy level is the fourth energy level. 4s2, 4p6. So I bet you could generalize. If you were a good skeptic and you wanted to write out the electron configuration of xenon, I bet you would find 5s2, 5p6. Radon would be 6s2, 6p6. Other than helium, which is a special case, there are 8 valence electrons for a noble gas, S2p6. Wait a minute, let's think about that. Before I go on to the next slide, notice that even though I have the D's here higher in energy than the 4 S's, they don't count as valence electrons. I'm looking at the numerical value of the highest occupied energy level. So we're distinguishing between valence electrons and core electrons. The valence electrons, I said before, are in the outermost occupied energy level. And that turned out we were only looking at the s and p orbitals at the highest occupied energy level. Those are the ones that affect the chemistry. The core electrons are hidden inside the valence electrons. They're too sheltered from other atoms coming in to react. It's the outermost valence electron that control the reactivity. So elements in the same group have the same reactivity because they have the same number of valence electrons. The reason why I started with the noble gases is because we know their chemistry. Noble gases are very stable because they have full valence orbitals. The valence orbitals are the s and p orbitals. S orbitals come in sets of 1. P orbitals come in sets of 3. So the s and p orbitals together make a set of 4 valence orbitals. Each orbital can hold 2 electrons. So when they have 8 valence electrons, they have full s's and p's. Let's go back to the previous slide and check that out. Each one of those noble gases, except for helium, have 8 valence electrons filling up the s and p. And you'll see that helium, although it doesn't have 8 valence electrons, fulfills the spirit of the configuration of noble gases. At the first energy level, there are no p orbitals. So helium, like the other noble gases, has full valence orbitals as well. So we're going to associate full valence orbitals with great stability. That's a very stable arrangement. That makes them unreactive. All right, with that in mind, we can go look at other groups in the periodic table. Let's pick a representative one. I don't want to write the configurations for every element in the group. Let's try sodium as my favorite alkali metal. Let's try beryllium as an alkaline earth metal, group 2. And let's try fluorine as a halogen. And I picked those ones because those have pretty small atomic numbers. And I don't have to waste a lot of time writing out long SPDF notations. I am going to write an SPF notation first. If you want to prove that you have this mastered, go ahead and do it. Pause the video. All right, for sodium, the electron configuration is 1s2, 2s2, 2p6, 3s1 to get 11 electrons. So the valence configuration ends in S1. For sodium, it's 3s1. I could look at any other alkali metal, and its valence configuration would be NS1. The N would vary. Different alkali metals would have different values for N there. What I see there is that alkali metals then have only 1 valence electron. Only 1 electron in the highest occupied energy level. All right, are you ready for this? Neutral alkali metals are so reactive you never see them in nature. They want to react to become stable. And we saw that they will become stable when they have full valence orbitals. So what they have to do is lose 1 electron so that they are left with full valence orbitals the next energy level down. Now, what charge does an alkali metal make? +1. It wants to lose 1 electron to become stable. Coincidence? I think not. All right, let's look at the alkaline earth metals, group 2. Beryllium, as an example, is 1s2, 2s2. The valence level for beryllium is the second energy level. I could look at other alkaline earth metals, and their valence configurations would end in Ns2. In other words, they have 2 valence electrons. You don't find alkaline earth metals in their neutral forms in nature either. They form ions. Well, what kind of ions do they want to form? If they lost 2 electrons to be left with just the full lower energy level, that would be a stable arrangement. What's the charge on an ion we get from a group 2 atom, an alkaline earth metal? +2. Coincidence? I think not. So, last example, last group, halogens. Fluorine is 1s2, 2s2, 2p5. So here's its valence level. If I looked at other halogens, they would end in ns2np5, and the value of n, again, would change for different halogens. How many valence electrons? 7. That's not a stable configuration. It wants to react to get full valence levels. If it picked up 1 more electron, it would fill up that p level. What charge is on a halide ion? -1. It picks up 1 electron. Coincidence? I think not. So what we can see, as we knew before, that ions form so that they are isoelectronic with the nearest noble gas. But we accepted that as authoritative knowledge a few chapters ago. Now we see why that is. Ions form to be isoelectronic as the nearest noble gas, to have the same number of electrons, to have the same electron configuration as a noble gas. And what that means is they react to get full valence orbitals. I am so glad we're getting the chance to have a richer understanding, because for me that makes the difference between memorizing and remembering. I might have memorized that they become isoelectronic with the nearest noble gas, but now that I know why, I can remember it and reconstruct that knowledge whenever I need it. So I'm really excited to show you the next slide. Do you ever wonder why the periodic table has that weird shape that it does? Would you have come up with that? Okay, check this out, my friends. When we looked at the configuration of the alkali metals and the alkaline earth metals, we saw that they ended in S1. And the alkaline earth metals ended in S2. Hey, we call this section of the periodic table the S block, because the configurations of the atoms end in S. Now, why is that block 2 columns wide? Because S orbitals come in sets of 1, and they can hold 2 electrons. Now this helps me remember, because you always get a periodic table with you. Nobody memorizes it, I hope. When you see that S block, it reminds you that S orbitals come in sets of 1 because it's 2 columns wide. All right, I'm going to rock your world. Are you ready? When we looked at the noble gases, we saw that their configurations ended in P6. When we look at the halogens, they ended in P5. Guess what block this pink block is? That is the P block. How many columns wide is it? 6. Coincidence? I think not. P orbitals come in sets of 3, 2 electrons per orbital. That gives me up to 6. And again, if I forget how many P's come in a set of P's, I just need to look at that P block that is 6 columns wide to know that there are 3 P orbitals in a set. All right, now you can anticipate me here. Guess what's coming next? Look at those transition metals. If I wrote the electron configuration for a transition metal, they would end in D. This is the D block. And how many columns wide is it? 10. Coincidence? I think not. Now, we looked at the configuration for iron. It ended in D6. D6, let's see. That's D1, D2, whoops, should be a superscript, not a subscript. D3, D4, D5, D6. This is why I can write electron configurations faster than you've been able to, because I know, looking at the periodic table, what the configuration should end in. You remember that we had a shortcut for, we had an exception for some of the ones that had one less than half full D or one electron less than full D. Well, that's D4 and D9, one short of half full or one short of full. So if you're looking for the atoms that were the exceptions we were looking at, they're going to be in this column that ended in D4, one short of half full Ds, or in this column, one short of full Ds. Pretty good, huh? One last block. Down at the bottom are the lanthanides and actinides in green. And they're written at the bottom just so that we don't have to make the periodic table too wide. Really, they would fit in here. S orbitals come in sets of 1, p orbitals come in sets of 3, d orbitals come in sets of 5, f orbitals come in sets of 7. Guess how wide the F block is? 14 elements wide. Coincidence? I think not. So now I don't need tricks anymore. I don't memorize periodic tables. I know how to use it. Just a little editorial comment about that. I've heard of teachers that make people memorize bits of the periodic table. Darned if I know why. I can carry the periodic table on a little card, or I can look it up on Google really quickly. The skill is to know how to use it. So instead of looking at the periodic table on the previous slide that's color-coded, I'm going to do this next analysis on the periodic table that I always give you. The F block isn't shown there. I would show you it if you needed it, but the lanthanides and actinides are their placeholders here. You can see that there's a discontinuity in atomic number from 57 to 72. The value of the energy level corresponds to the row. For the first row, the configuration, the valence level is the first energy level. Second period, valence or electrons in the second energy level. Third, fourth, and so on. And we already looked at the S block and the P block and the D block. So now I can use the periodic table instead of that trick with the diagonal arrows. I'm not going to do that anymore. To follow the order of orbital energies. I'm going to start with hydrogen. That's in row number 1. What comes first? 1s. After 1s, okay, helium's a special case, that fills the orbital. After 1s comes 2s. And after 2s comes 2p. And after 2p comes 3s. And then 3p. And after 3p comes 4s. And after 4s, hey, we're in the D block. Now, if there's a little trick, this is going to be it. The 4s is followed by the 3d. And the way I think of that is that the d orbitals first came in at the third energy level. So the first row of the D block is the 3D. After 3D comes 4P, and then 5S, and then 4D, and then 5P, and then 6S. And then, oops, here's the first one in the F block, 4F. F orbitals first appear at the 4th energy level. Then we go on to the 5D and the 6P, and so on and so on and so on. So I just look at the periodic table, I know the order. Here's another cool thing. Let's pick a particular element. Let's go for arsenic, number 33. I can tell you what that electron configuration should end in just by looking at its position in the periodic table. It's in the 4th row, so the configuration is going to end in 4. It's in the P block, 4P. Which column of the P block? It's in the 3rd column of the P block. So if you were going to write the full electron configuration of arsenic, you can double check that you're right because it should end in 4P3. Pretty cool, huh? Here's another thing we might want to know. We might want to know how many valence electrons an atom has, because that's what affects its reactivity. You'll remember that the definition of the valence orbitals were the highest occupied S and P. So to count the valence electrons, I'm just going to count across the S and P blocks. How many valence electrons does arsenic have? Here we go, counting over the S and P blocks. 1, 2, 3, 4, 5 to get to arsenic. Arsenic has 5 valence electrons. And one last thing to show you. I showed you a noble gas abbreviation in the last video. And that didn't seem like much of a shortcut if I had to write the full configuration to abbreviate it with the noble gas. But now for arsenic, all I have to do is go back to the noble gas before it. And if I write argon in square brackets, that means the electron configuration of argon. To write the rest of the configuration, I just continue on. After argon 18 comes krypton 19. And that's in the 4s block. 4s will hold 2. To get to arsenic, I have to come over after the 4s to the 4p. 4p3, as we said before. Hey, look, 5 valence electrons. Ta-da! So, you will now understand the structure of the periodic table. You can use it to find its valence configuration. And in the next video, we will relate that to its chemical and physical properties. This is Finally Chemistry. Thank you for your patience.